Introduction on aquaponics. So we know soilless cultivation is a millennial principle. We didn't invent anything. Chinampas in the Aztec civilization were created 1,000 years ago, where they just cultivate plants on lake or on different water surface, with multiple layers of substrate, woods and sludge assembled together to make a fertile soil. Also, for the integration of aquaculture and agriculture, it's quite a long story. Pisciculture in China was invented many years, 1,000 years ago. And we can see there one maybe of the first very large-scale aquaponic system. It's in the Taiyu Lake in China. This lake had a lot of problems with pollution. It was all green everywhere with algae, and they managed to make phytoepuration on this eutrophic lake on 16,000 square meters of rafts. So it's quite impressive. So the conceptual scheme that you all know, but it's always good to make a little presentation. So in the aquaponics system, you have the fish feed as a source of proteins, lipids, minerals, vitamins for fish. You have a RAS, usually, which is a nearly closed system, but as I said, it can be quite open, quite closed. There are different types of RAS. It produces solids and dissolves the nutrients. So you have all the nitrification process inside the mandatory step of biological filtration. The dissolved particles coming from the nitrification and also the natural mineralization occurring inside the system can be then assimilated by plants. After also a mandatory step of mechanical filtration for solids removal. It can be with highly technical solution like this one, what do you call that, drum filter. You can also have an optional step of bacterial mineralization. That's what we would like to develop in APIVA later. So the plants take off the nutrients from the water. And with oxygenation, gas stripping, and makeup water, you can go back to the fish, and it allows to recycle 90 to 99% of the water. What kind of fish you can use? I will focus on France, example. Actually, in France, we are not allowed to use many types of fish. It's a problem for project holder because we don't have many choices. There is a difficult administration in our country. So we can use carps, trouts, sander, silure, it's a kind of catfish, ornamentals, perch, sturgeon, lobster. There is a list of species we can use, so it's written there. So I will talk later about the regulation in Europe and why is it different in France. Then which plant can be cultivated? Almost everything, but with some plants it will be more easy than others. For example, all leafy greens works very well, ornamentals also, but tomatoes is another problem. But we will discuss about that. Maybe some of you have tried more complex vegetables and can tell us about that. The advantages and drawbacks of aquaponics. There is metabolic fish waste valorization. It reduces the waste. You double use your fish feed for double production. You can reduce or delete, when it's sized correctly, the use of synthetic fertilizers. You can recycle the water. So it's a soilless cultivation, so you usually have a better yield per square meter. Some studies shows that aquaponics can be a method for diminish some kind of mushroom, pathogen mushroom like fusarium, and it also simplifies a lot cultural techniques and it's less work than in conventional agriculture, where you have to labor the soil and everything. It's well adapted. Sorry for the mistakes here. Well adapted to short food supply chain, and all about urban and peri-urban agriculture. And you can also do that on non-arable soils, which is a very good argument for aquaponics. And you can also rely on space optimization with vertical culture, and you can share the cost of infrastructure with for two activities and two different producers. You can have two activities working together, but each one owns his part. The drawbacks is that we don't have much scientific references on technical data. Actually, we have more and more now, but for the moment, it's not clear to know how you should size your system in order to make it work properly. So it's going to change maybe. It's a significant investment for project holder, and there are high production costs, mostly on energy and personnel. There is a need also for economical data, because for the moment we can say, okay, aquaponics is profitable, you should go in work in aquaponics. We don't have the possibility to use the organic label in Europe for aquaponics. This is a problem also, because how you can value your products with which label, or you can communicate on it. And you usually have to find a niche market in order to make your business work properly. Actually, that's what we saw in the different commercial structure we visited in the framework of APIVA. And also, it's very complex to manage. You need skills. You can have a lot of on-call duty, and you need to make a lot of maintenance and monitoring of the system. And then the societal limits. There is not much step back on the perception of consumers on aquaponics product. But we have now some first elements that shows that it shouldn't be a problem. It shouldn't be a cultural problem. And there is no clear regulation to date about the status of aquaponics, the status of the irrigation water we use. Are we allowed to use fish effluents to grow plants and then sell the plants? What is the status of the producer in aquaponics? Is it a fish farmer or plant grower? Can he has two administrative status? So this, I won't talk much about it. You all know that. The most used technique associated with aquaculture, the raft techniques, nutrient film technique, and media field build technique. And more you have also a vertical system like zip grow or aeroponics, but I don't have much step back on aeroponics use on aquaponics. I don't know if you heard about it. Then we can talk about the different kind of aquaponics system that exist. The classical system is what we call the coupled system. So we have the fish tanks, the mechanical filtration. We extract the sludge, and we can also mineralize it. Then it goes to the biological filtration. Then to the soilless compartment, which can be different techniques. And then it goes back directly to fish tanks. But more and more, at a commercial scale, mostly we saw the development of a decoupled system, because the coupled system has some limits because of the total independence between between the two compartments. It can be quite dangerous at a big scale if there is a problem in the fish part or in the plants part. So that's why some people develop what we call decoupled aquaponics system, where you have the fish RAS part and the plants part. They are linked, but decoupled. So you can couple it if you want. And if there is a problem, you just decouple, and The plant's part can work by itself, for example, with added nutrients if necessary after some days. And then you can do what you want on the fish RAS system, for example, if you have diseases on the fish. Because you don't want to add antibiotics, for example, in your fish, and then it goes in the plants can accumulate it. Same thing for pesticides, so most of the time you will use biological control, but if it doesn't work, maybe you don't have a choice, you use conventional products, and then you don't want pesticides to go in the fish. That's why decoupled system seems a good idea at commercial scale. It allows security, flexibility, ability to make the system independent, and it also allows a system, an hybrid system. Some people do that, for example, in Germany, in ECF farm system. It's not a real aquaponics system since they add nutrients. There is a buffer tank where they add nutrients for growing tomatoes, for example, because it will not work properly in only aquaponics. A decoupled system also allows two professionals to ally their skills and work together. So you have the fish farmer and the plant grower on the other side. They work together. The one is using the waste of the other, and it's a good system. Now about the problematics. So I have 45 minutes for everything. Okay, challenge accepted. So aquaponics is all about finding a compromise in temperature between different species working together. So the fish and the plants both have favorite temperatures to work in, and biofilter would prefer warm to hot temperature, 15 to 30. The oxygen level for fish farming, it's really different between species. Cold water species will need a high concentration in the water, but fish like tilapia or carps will be happy with only 3 milligrams per liter in the water, even if it's better to have more. For plants, you need also to have enough oxygen, and biofilter also. So you have to evaluate the needs of every part of the system when you size it, and also anticipate the evolution of temperature you can have in your system, since it affects the concentration of oxygen you have in the water. Then for the pH, the best pH for aquaponics should be 6.5 to 7, because it's the best compromise between the three. Plants prefer low pH to assimilate the nutrients better. Biofilter prefer very alkaline pH, and fish farming, they are happy all the time between 6.5 and 8.5, so they are the less problematic in this situation. Also the alkalinity, you need to have enough alkalinity in your system, because it's the buffer power, and you don't want your pH to go down in 5 minutes. So you need to have an alkaline reserve for bacterial nitrification, and you need to learn how to manage the pH daily. And then the conductivity. I don't have really an idea of what is the better conductivity for fish farming and biofilter, but plants prefer this scale of conductivity. That's what we find actually in hydroponics, but in aquaponics we never managed to reach this concentration, this conductivity. And it works pretty well at 600 to 1000 millisiemens per centimeter. So the biofilter is the hub of the system. Here it's interesting table if you want to keep it. Just how to go from a form of nitrates on the other form, because in between publication it is expressed in NO3 or NNO3, the same for the other nutrients. So you just multiply by the coefficient. Then you have the nitrogenous form levels of tolerance for fish. Ammonia, gaseous ammonia, ionic ammonia, nitrate and nitrates. And there, maybe you see it, yeah. I put some ratio of how to evaluate the total ammonia and nitrogen produced by the fish. It's between 35 and 50 grams of total ammonia and nitrogen per kilo of feed input. But it's in function of the protein rate of the feed. So for 32% of protein, it would be more 35, and for a high content of protein in the fish, it would more be 50 grams per kilo. And then the total ammonia and nitrogen treated by the biofilter in gram per meter carré, per square meter per day, which is in function of pH and temperature. Then oxygen is also problematic, both for fish and for plants. For the plant, it will induce stomach. If you don't have enough oxygen, it will decrease the photosynthesis and the evapotranspiration because of the stomatal closure, and it will also decrease the absorption of elements. And for the fish, if you don't have enough oxygen, it will be very fast. Actually, they will die. So you need to promote oxygenation through implementing cascades, water brewer, and the design must be, as I say, based on the fish and the bacteria's needs. Then for the plants, it's more complicated to evaluate. So just add brewers in your growing tanks. Okay. Then the electrical conductivity. This table was given by a research center in soilless cultivation, CTIFL. They told that the conductivity, when the conductivity in the substrate is at 2000, so in aquaponics we are much lower, you will have less coloration, firmness, preservation potential of the product, but more production compared to high conductivity. But the question is, at very low conductivity, what happens about coloration? So we can see sometimes that the lettuce are less green than in hydroponics. They are sometimes more weak when we touch the leaf. And about the preservation, I don't have really an idea on that. But the production is quite okay with low conductivity. The maximum conductivity we reached in APIVA was 1,300 millisiemens per centimeter, which is quite high. But the question we asked is what about the quality, the taste, and the preservation of the product? So work is in progress on that, but we can say that for the taste, there is at least no problem because of the sensorial test we made. Then this is the availability of element as a function of pH. So the width of the strips indicates the level of assimilation of each nutrient, and we can see that, for example, phosphorus, manganese, bore become very less available when pH is higher than 6.5, and you have a risk of deficiency on these elements. But not only, we saw deficiencies in potassium and iron. This is how it works in the roots. At a growth stage, you have a high concentration of high consumption of nitrates by the roots. And when the plant grows during the production stage, there is a little less NO3 and more K+. And so at the growth stage, you tend to increase the pH in the root solution because of that. And at the production stage, you decrease the pH. Yeah. So how to maintain the pH of the water and how to avoid the pH to go down or to stay too high. First, we have to know that nitrification consumes alkalinity, so it makes the pH go down. So you never need to add acids. Also, nitrifying bacteria feed on inorganic carbonates, oxygen, and a different form of nitrogen. So you usually have to use daily pH buffer, so it can be potassium bicarbonate. Some use sodium bicarbonate, even if it can accumulate sodium in the system, or CrCO3 or lime. But in some system, you never have to add a buffer for the pH. For example, in Rato, it's been like 4 or 5 months that we haven't added anything because makeup water is really alkaline. So it will really depend on the water source. And it's very difficult to keep the pH between 6.5 and 7 because when the pH is under 7, it will go very faster because of the low alkalinity of the water. And also you have to determine in each kind of system, in each situation, a good ratio between makeup water and feed intake to have this stabilization of the pH in the desired range. So about fish food, fish feed, which is also the fertilizer for plants. It's mainly vegetable and fish meal ingredients. There is variable requirements between species and between physiological stage of the fishes. Some studies shows that concerning the metabolic waste, we have only 20 to 50% of the nitrogen that is really assimilated by the fish when the feed is eaten. And for the phosphorus, it will be between 15 and 65%. So that shows how much this can be a problem in recirculated aquaculture without any treatment of the water with plants or something else, or denitrification, for example. If you don't epurate your water, it will accumulate more and more. And the problem in RAS is that, okay, you consume less water, you have less effluent, but it's a very concentrated effluent. Sufficient quantity, it becomes a limiting factor for the development and production of the crop. But also an excessive amount of certain nutrients can lead to a decrease of bioavailability because of different interaction between some nutrients like K, Ca, and magnesium. If you have too much potassium, you will not be able to assimilate calcium and magnesium, and the same rule for each of these three. Then, okay, no, this is not very interesting. No. So in aquaponics, the plant food comes from the dissolved water from fish metabolism and the solid mineralized waste with the activity of heterotrophic bacteria. So it can occur naturally in the system, but you can also add mineralization tanks to optimize the mineralization of your solids. As we said, the existing fish feed for now is not really optimal for plant nutrition. For leaf plants, it's quite okay. You are satisfied with a low electroconductivity to succeed in your growing. But for fruit and vegetable plants like tomatoes, it's more complex, and you can expect deficiencies or low productivity because of the lack of iron, phosphorus sometimes, and potassium. But you can add chelatid iron, which is not toxic to fish. I saw on technical sheet that you can go up to 200 milligrams per liter of chelatid iron inside the water. But okay, you shouldn't try. But it's a level that begins to be dangerous for the fish. So if we put 2 milligrams per liter in the water, it should not be a problem. Potassium bicarbonate is usually used for pH management. It's a bit expensive compared to sodium bicarbonate, but at least it can add potassium in your system, and you don't want to have too much sodium in your system because of the plants, but don't really like it. And what about the other nutrients? Phosphorus is a problem, I think, in aquaponics, because it can very fast become limiting. If you don't, so that's why it's relevant to try to take the phosphorus from the sludge, because it's highly concentrated in phosphorus inside the sludge. And also because phosphorus, researchers say that in 50 years we won't have any more phosphorus in the world. So maybe it's true, maybe not. But the tendency is to use the phosphorus, to optimize the use of the phosphorus in agronomic systems. Then, if you put fertilizers in the water, is it compatible with fish? If you make a totally coupled water with added nutrients inside, can it be a problem for the fish health? We don't really know. For now, that's why many people use a decoupled system to make hybrid aquaponics. So it's mostly at commercial scale, intensive production of plants and fish. Aquaponics can work very well at extensive scale. So it's really a choice. Do you choose the quality? Do you choose the quantity? What are your arguments for marketing your products? Then about the nutrient deficiencies, you need to get to know the mineral elements contained in the water coming out of the fish tank. That's the first thing. Also to know what is in your makeup water. It can be interesting. Some makeup water can be very rich in, naturally rich in different micronutrients. You should prefer maybe leafy vegetables which require the lower and more constant mineral requirements over time, because plants like tomato have very different needs between the first stage and between the fruiting stage. They don't have the same nutrients needs for all their production period. That's why it's difficult to make it in aquaponics. That's what I put it. It have fluctuating needs. Managing the hydroponic circuit in parallel with the fish one in decoupled configuration is more flexible to manage mineral elements that you add in the system if you don't want to take the risk to affect your fishes. However, after all that is said, experience shows that sometimes we are surprised, because, for example, Catherine made strawberries in aquaponics, and it had very high productivity, which was comparable to conventional production. So it was only aquaponics with nothing added. So I think the bacteria's factor is very important in aquaponics, because it can help a lot to the plants to take all of these nutrients out of the water.